Should have got that on record. Okay. So this first test is the shortest of the three, and we can make it in our normal class time. But in the other two exams, we're going to have other arrangements so to give you like 90 minutes, and we'll work that out. If there's individual issues, we'll get those worked out. But this first one, let's just start at, we'll come 5 minutes early. We'll start at 10:40, and we'll go till 5 minutes late. So we have a full hour, okay? So we'll start 5 minutes early, and you can have 5 more minutes after class ends. So I guess that makes it what? So 10:40 to 11:40. 10:40 to 11:40, that'll be Friday. Friday, not Wednesday. Okay, so this problem seemed to be causing difficulty a little bit. So let's look at this one. I'm going to find the distance from a point to a plane. It's odd. The light is on, but it's not working. Oh, there we are. Okay. So we got some plane. So with these problems, these are geometry problems. Draw pictures. Draw pictures so you can visualize, understand the situation. You don't have to, but you can. Your picture can be perfectly useful without drawing the exact plane, negative 4x plus y minus 2 is equals 4 in R3. You don't have to get the inclination and all the points right. Just throw a plane up there, throw a point. Apart from the R3, getting all the R3 coordinates right, and it's still just as useful as a picture. So we're trying to get this distance. And this is the plane, negative 4x plus y minus 2z equals 4. So we've got lots of tools now, dot product, projections, cross product. How are we going to get that distance from that point to that plane? So what's a starting point here? So looking at the plane, what could we get from the plane? Yeah, we could get a point on the plane, and we can do that easily by, what do you want to plug in? Yeah, just go 0, 0, remember? 0, 0 in this case. Negative 2. Now will that be that point right there? No, maybe, very coincidentally, but probably is not. So here's this point that we found on the plane, 0, 0, 2, negative 2, sorry. Okay, what else could we do here? So I got the point Q is 3, 3, negative 2. So I've probably done this kind of problem before. I don't remember what I did before, but this is kind of the idea, is that you just kind of figure it out as you go, and then you try stuff, and if it doesn't work, then you try something else. But if what you try works, you got to do the math right also, right? You got to do the numbers right. So there's both aspects to it, yeah.
Since point Q is going to be perpendicular to the plane, since it's the shortest distance there, we can make a right triangle from PQ to that point.
Okay. Do we know this point though? Yeah, we don't know this point. But yes, absolutely, we can make a right triangle. We just don't know this point. The point is here. Okay, other ideas?
We could get the vector projection.
Except that onto what? Yes, but onto what? Right, so the vector projection of PQ, is that what you're thinking?
Yeah.
Like we can find that vector PQ, yep. And yeah, we'd love to project it onto this plane, but all I've got is this point. Yeah.
You can project it onto the vector that is perpendicular to the plane, and we know that from the equation the vector
Oh, cool.
is negative 4, 1, negative 2.
Very good. So from this plane, then we have a normal vector, which is negative 4, 1, negative 2. And so that's parallel to this dotted line right here. So I've got this vector And so with that vector, do we want to project PQ on, we can project the vector PQ onto the normal vector to the plane. Does it work? Because if we did that, no matter how big this vector is, it's still, it doesn't matter what this magnitude of this is, right? The projection will be the same. Do you see that? This could be 100 miles tall, and the projection will still be this. This could be a millimeter tall, and the projection of PQ onto that thing will still be this. Does that make sense? Yep, that's true, right? Because when you project PQ onto something else, it's really, you're just projecting it onto a direction. You're projecting it onto like a line, right? Yeah, so that would be how to do this. So we can get the vector PQ and do the vector projection of PQ onto the normal vector. And actually, we just need the scalar projection, right? Because that's asking for the distance. So we just do the scalar projection. Or the vector projection and find the magnitude, but then you're doing more work than you need to do. Okay, so I won't, for time's sake, I won't finish that. Does the roadmap for this problem make sense? Could you finish it? If you got a question, don't hesitate to ask. Okay. Well, maybe let's just glance at one more here. Three or seven? Meeny, meeny, miny, mo. 7. Angle of intersection of planes. So we've seen the angle of intersection of planes before on a previous assignment, didn't we? Didn't we see angle of intersection of planes? I remember answering this question. Oh no, it's the online. Sorry, online course is half a semester long, so it's accelerated. That's why. So I was answering that question. So no, we have not seen this. So suppose that I have this plane. I'll just draw. Again, you don't have to draw the planes with the correct orientation in R3. You can just make a picture. This is a trickier picture, but we'll do our best here. That's terrible. Let's see if we can do better here. I'll make it more upright. So there we go. So when it comes to the angle of intersection, so really there's two angles, right? Unless they're at 90 degrees to each other, then all the angles are right angles. But if they're not at 90 degrees to each other, then there's really two angles, right? So what they mean when they say angle of intersection, it will always be the smaller of the two, the acute angle. So you may do the math perfectly correctly, and you'll get an angle greater than 90 degrees, an obtuse angle. So it's not, you didn't do anything wrong. It's just that the angle of intersection, quote unquote, is the acute, is its complement, the acute one. So I'm saying, so this is a little bit less, looking like a little bit less than 90. So that's the one that we want. So how are we going to find that angle? How are we going to find that angle? Idea, yeah.
Since we have the direction angles, or the direction vectors of each of the planes, we take the, I want to say, dot product of them.
Okay, so so this is plane R for red, and that's we got the normal vector of that one. What is it? Say 1, -4, 2, right? Mm-hmm. And then this one is plane G for green. Its normal vector would be something like this. See that? So what about the angle between those vectors? Does that the angle between the planes? Do you see that those two vectors then, as they come together tail to tail, are just rotated 90 degrees from how the planes are oriented. So yeah, so you just need to find the angle between the normal vectors. So this angle right here, this angle right here is the same as this one right here. Just imagine taking those two vectors and just rotating them back 90 degrees, then they would lie in their respective planes, right? If I rotated that back there, it'd be in its plane, and then that angle would be the same as this angle. See that? So then the question is, how do you find the angle between two vectors? Remember that? That's an important technique. You all should know that. If you have two vectors, how do you find the angle? I know these two guys know. How about in the back? How do you find that? Yeah. What's that? Okay, but then, but that's our unknown, right? So we don't know what that is. How am I going to find that?
Take the dot product of the two vectors, and then you take the magnitude of both vectors, and you divide the dot product.
Yeah, is that what you're thinking? Yeah, that's equal to, so this is one way to find the dot product, right? The other way to find the dot product is by the multiplying and adding, right? The multiplying and adding. So if you multiply and add, that equals this way of finding the dot product because they're both the dot product. And you've got the magnitude of each, and the only unknown then is your theta. So we use the dot. We use the two ways of computing the dot product by setting those equal. That allows us to solve for the angle. Okay, so this one's due at 5 o'clock tonight. Those are some tips for you. Any questions? Yeah.
How would we enter it into the toolbar? Because I did it on hand and then I did it with the calculator and I got the same answer, but the problem was telling me it was wrong.
Okay, was it greater than 90 degrees?
I tried both of them, the big one and the small one.
So then there's this error in your math somewhere. Yeah. So it should be the acute one. It should be the one less than 90 degrees or less than 5 or 2.
Okay.
Did both the radians and the degrees were wrong, or just degrees?
Both.
Both were wrong. Yeah.
But so it confusing. What if you just put it in radians and degrees?
So in radians, we can get it exact. Use pi, right? So pi, and you can put an expression in there. And don't use your handheld calculator. So that let it be your calculator. And then once you get that right, then it's a matter of getting it in degrees correctly. And you could do a formula with that, right? Just do a conversion from radians to degrees using pi and 180. And again, you could put an exact answer in for degrees as well. But no, actually, so you're using like arc cosine, right? So how do you do arc cosine?
You can do cosine raised to -1, or you can write in arc cosine.
Operations, inverse trig. This one, you're going to be using that one.
Cotangent?
No, not cotangent. Inverse cosine. So it goes in, so you're going to just leave that as it is, and then you're going to put your argument in here. But then it'll be a more complicated expression than that, right? The cosine inverse of your A dot B expression divided by your magnitudes multiplied. So that way, don't use a handheld, and then you'll know if you'll know it has nothing to do with like rounding error or punching error. It'll be something with what you did if you do it this way. Okay, other questions? Okay, so let's press on to the next topic here. So remember what the difference between a plane and a line was? Yeah, plane has 2 kind of degrees of freedom, right? A line has just 1 degree of freedom, and so that made our plane ended up being an equation of x, y, and z. Now we've seen another thing that has kind of 2 degrees of freedom and was an equation of x, y, and z. Is that what you're gonna say? Yeah. So they're both saying sphere. That's right. So those are the 2. These would be surfaces, right? So far we've analyzed 2 different instances of equations of x, y, and z, spheres and planes. our basic form of a sphere was x minus a squared plus y minus b squared plus z minus c squared equals r squared. ABC was center, r is the radius. Our plane, we had when we're given planes, they often look like this. And we know you guys are experts at planes. If you're asked to write the equation of the plane, you use this other formula, right? Where you just plug in the point and plug in the normal vector. But when you're given a plane, most of the time they're given this way, right? So you'd have to know how to generate points, know how to do that, right? Given a plane, know how to generate lots of points on that plane. So this is the idea of surfaces. Equations of x, y, and z, they express all ordered triples in R3 that form a surface in space. So spheres and planes are like apples to apples, right? They're both surfaces in space, so their mathematical representation is similar. An equation of x, y, and z. A line is a different animal, right? And so it doesn't. You don't have an equation of x, y, and z for a line. What you have is a vector equation of one variable t. But today we're going to focus on surfaces, two of which we know already, spheres and planes. All right, so first is ellipsoids are simply a more general version of a sphere, like a sphere that's stretched or smushed. So we can start with our equation of a sphere, like this. We can start by dividing both sides by r squared. And what would we do now to smush or stretch it? What would we do? Yeah, so now change these r's per the x, y, or z component. That would stretch or smush it. So we're going to allow different radii, I shouldn't say on each axis, but in parallel to each axis. So allow a different radii parallel to each axis, and then the formula becomes this. You got like a x radius and a y radius and a z radius. And that's what we mean by an ellipsoid. So you get things like rugby balls and pills and UFOs. Any way you could, watermelons, right? You could take any way you could take a sphere and kind of compress it or stretch it in multiple directions. So you get these kind of oblong shapes. Okay, so let's analyze what this is here. So if we want to make this look like our equation of ellipsoid, it would be, how does this relate to that? It's really x minus 3 squared over what? 1/4, right? Plus y squared over 9 plus z minus 2 squared over 1 squared. So what's my x quote radius? It would be 1/2, right? If this is r squared, then in the x direction we'd have like a 1/2 radius. In the y direction, 3. Z direction, 1. Okay, so what's the effect of x minus 3 instead of just x? So to get the same, what do we have to do to get the same x coordinates that we had before? What do we have to do to all the x values to get the same x values we had if it were just x squared? What would we have to do to them? Add 3, right? So then what does that do? That moves it 3 in the positive x direction. Because to get x squared over 1/4, for this one, all the x values would have to be 3 greater. Well, that's moving which direction in R3? Forward, right? Out towards you. Yeah, out towards you guys. So now rather than the center being 0, it's out 3 here. And in that direction, radius is, said, 1/2. So just a little, so we can go forward and back 1/2, okay? And then the y direction, first of all, it doesn't move left or right at all, but our radius is 3. So we're going to be out here and back this way, 3. Oh, but I should have done this before I did that. I should have, what, z, and we're going to go, what, up 2, right? So forward 3 and up 2, and that's going to be the center of the ellipsoid. So the center of the ellipsoid is 3, 0, 2. So it's going to be really scrunched in the x direction because its radius is 1/2. It's going to be stretched in the y direction because the radius is 3 in that direction, and then z is just kind of where it was before. So what will that look like? So up 1, up 1 and down 1, over 3, and over 3, and then back 1/2 and forward 1/2. So those are like the key points, like the poles, right? The north pole, the south pole, the front pole, the back pole, the left and the right pole of that thing. So now I'm going to try to draw it. So parallel to the YZ, something like this. I guess that's something like that. Part again. Better, okay. And then forward, just a little bit forward. And then, again, just a little bit forward here. So stretched mostly in Y, smushed in X from a radius 1 sphere with a center of 3, 0, 2. So like a pill, not a pill. Okay, questions on that? So ellipsoids are just, a sphere is a special case of an ellipsoid where all the radii are the same. Or an ellipsoid is when you smush or stretch a sphere. Okay, so that's easy. So now we got another surface added to our repertoire, and that's ellipsoids. Okay, so now when we go on to other surfaces, we want to talk about something called traces. So by setting one of x, y, or z to different constants, the remaining equations of two variables create curves in space. And those curves in space that lie on the surface, right? Curves in space that are all curves that are totally on the surface, we call those traces. They're tracing on the surface. Okay? And if you've got lots of traces, what you get is kind of a skeletal structure of that surface, like a net that would lie on the surface, and so then you can imagine the whole surface in your mind. Okay? So in order to draw traces, then you need to be good at just basic curves in R2, because we're eliminating one variable basically, and we're left with an equation of two variables. That's like a curve in R2. So this is here kind of a summary of curves in R2. So parabolas. So now u, v, and w, or u and v are any two variables of x, y, and z. So I can pick any two variables of x, y, and z, substitute those in for u and v, and this would be my general form of a parabola. For instance, x minus 1 equals 4 times y minus 3 quantity squared. That would be a parabola. But then I could have, u could be z and v could be y or whatever. So there's my general form of parabola. Circles are just like spheres, but with one less dimension. Again, u and v could be any of x, y, and z. Ellipses, again, like an ellipsoid, but in two dimensions. U and v could be any two of x, y, and z. Hyperbolas, we won't work too much with these. We're going to avoid these a little bit, but you may see a few in the homework. Those are the same, it's the same formula as an ellipse, but with a minus sign. Those will only show up occasionally. And then lines, of course, is just linear relationship between any two of those x, y, and z. So I kind of alluded to this earlier. What is the rule of the a and the b in any of these, right? So I'm always u minus a and v minus b. So what does a do to the trace?
So it's a center x, or if we're treating u as y, that would seem like a central y coordinate.
Okay, central y coordinate. Or what's another way? That's true. What's another way to think of it? Like central from where? Where did what used to be central? Origin, right? 0. So then this a is like translating, right? So it's like moving it. It's translating it a positive units of that or a negative units of that? Positive, right? Because with u minus a, all your u values have to be a bigger to get to be what you were before, right? So to be centered at the origin, all your u values would have to be an amount a bigger. And so that's bigger means going in the positive direction of that axis. Same with this. So the role of a and b are translation from the origin to ab. Okay, so does it make sense? Okay, so let's look at, so for something that's unfamiliar, we can build a contour, build the trace lines, right? So we can build the trace lines, also sometimes called contour lines. We can build those lines. So here we're going to do that, and we're going to do that. This is our first kind of unfamiliar surface, and that's going to be a y equals, z equals x squared plus y squared. And we're going to use traces to figure out what this is. Is it a surface, first of all? Is it a surface? Why is it a surface? An equation of x, y, and z, right? An equation that brings together x, y, and z will always be a surface in space, like a sphere or a plane or an ellipsoid that we've seen so far. So this is some surface, but it doesn't match any of those that we have. It's not a plane, it's not a sphere, it's not an ellipsoid. So what we do is, like I said, to do traces, we're going to start with letting x be constants. So for instance, if I let x equal 1, then what equation do I get? I get what? Z equals y squared plus 1. All right, and so that is a curve, right? That's a curve of z and y. And then that curve is going to live in the plane x equals 1 because we set x to be 1. So what is z equals y squared plus 1? What is that? So over here I can sketch that. I can just like have this be the z y-plane. What is z equals y squared plus 1? Parabola. Key point. Right. So is that z equals y squared plus 1? So let's sketch that. And then, so this is a trace of my surface. And where does this trace, besides living on the surface itself, it also lives where? In x equals 1. Because that's where it came from. It came from the fact that x equals 1. So what does that look like? So the plane x equals 1 is 1 unit out in front of you. See that? And so then in the plane of x equals 1, showing up good? Yeah. In the plane x equals 1, we have this curve, z equals y squared plus 1, and that is one trace on our surface. So now I'm going to take attendance, and you're going to find other traces for other x values. And you can try keep them close to 0, okay, and make them whole numbers. But try lots of different values. Or near 0 and whole values. You don't have to do crazy decimals or anything like that. But just you get the corresponding equation, and then you're going to imagine that that curve that you get, it lies in the plane of x equals whatever x value you chose. All right, so is the task clear? Does it make sense what we're doing? So you're going to find several traces by setting x values to different constants. You're going to find the corresponding traces. Go. Z equals y squared, right? So that's this one. And where does it live? In the yz plane, right? In the yz plane, you get that parabola right there. Anyone do -1? X equals -1. Did you do -1? What do you get? You get the same one we did the first time, right? So even in the plane x equals -1, it's back to that same parabola we found the first time. So can you imagine these? -1, 0. All right, anybody do -2? Yeah, Jacob, what'd you get? 4 plus y squared. So in the plane of -2, we get 4 plus y squared. Anyone do +3? Y squared plus 9, right? So it looks like this, way out. So 3 units in front of the screen or the YZ plane, you get y squared plus 9. So now you imagine all of those taken together, right? For all these different x values, taking all those together, and you get something that looks like this. Is that what you imagined? You should have imagined this. So even with just, what, how many traces is this? 5 traces, 6, 7 traces? You already start to see what this kind of looks like. And then we could do all this. All right, so the next thing I want you to do now is do constant z values. This is a little different. So let z be constant values, see what you get. And then you're going to sketch those in what? Z-planes, right? Constant z-planes. Go. And keep them, easy numbers. Around 0, whole values, okay? Okay, Travis, tell me one that you did.
I did z equals 1.
Z equals 1, got?
Z equals 4 and z equals 9.
Okay, for z equals 1, what'd you get?
I got 1 equals x squared plus y squared, which is a circle.
Circle radius 1, and where does that circle radius 1 live?
On the z equals 1 plane.
Right, good. So z equals 1, you said you get the circle of radius 1, start at the origin. And where does that live? And what is this equals 1 plane like? What's that like? Horizontal, up above, right? Is that right? So that's our, when z equals 1, that's the trace you get for z equals 1. Traces that are for constant z values have another name. They're called level curves. Okay? So when you do, specifically when you do traces where z is constant, it's called a level curve. Why? Because you're always on that curve, you stay at the same level, right? You stay at the same height or level. So level curves are a specific type of traces. All right? Who did something else? Let's see here. Somebody new. Sammy, did you do another z value? Z equals 2. All right, and what'd you get for that? And tell me about that. Okay. Is it radius 2? Rad 2, right? Radius of rad 2. So it's going to be up in z equals 2, and it's going to be a little bit bigger than this one, right? 1.4 or something like that. So that looks like this. I'm all over the place here. Let go, let go. Okay, here we go. So this is in the z equals 2 plane. Radius, radical 2, or 1.4 or 1, whatever. Okay, anyone do a negative z? Yeah, Matt. Negative 1, what'd you get? Right, negative 1 equals x squared plus y squared is undefined, right? There's no ordered pairs x and y that can make this thing be 1, negative 1. So then what about, so what's the conclusion for the graph? Yeah, so it won't work for any negative z values, so you won't find any points down there. None of the surface will lie down there because it doesn't make the equation work when you try to put a negative z in. So for different, so here's 2, 3, 4, 5, 6, etc. So it only works for positive z values. What about z equals 0? Does it work? It's the point, just that point, the origin. Okay, so then putting all those together with our ones from before. There's the level curves, right? The traces for constant z values. Let's put the x ones, the parabolas we got from before. All right, and what would happen if we let y be constant values? It would be a lot like what? The x's, they would just run in y planes, right? These planes. So I'll turn those on. So now you get a really good idea of what you have in between, right? So in between the curves, if you let your eye fill that in, you basically have, it's kind of like the tip of a rocket striking the ground, right? Something like that. But then that rocket will go on forever, right? So that rocket keeps. Okay, so this is what we call, so it's based on what two shapes? Yeah, parabolas and circles. So this thing is called a circular paraboloid. Circular because the cross sections are circles. Paraboloid because it's parabolic in the other two directions. So now I can turn on the whole thing. So we know it's not just those, it's not just the net, but it's the whole surface. It's all the points in between too. Try gray. Maybe gray will be better. Yeah, the traces form a net, and that net will lie on the surface and give you, and your brain will fill in the rest. You know, your brain knew exactly what that thing would look like when I turned on all the points, right? Okay, so let's talk about paraboloids here in terms of the equations. So there's there's basically three variations. We can, so this one, how does this one open? This one, like, what's its orientation? How does it open? Positive z direction, right? It opens in the positive z direction. So one alteration we can make is the direction in which it opens. Another alteration is translation, and we know that's just like x minus something, y minus something. We'll just move it. And then the third alteration we can make is mess with the radius of the circles, like, and stretch or smush it, so it's no longer circular, but it will be, instead of circular, it'll be elliptical. So then, if you mess with the radii of the circles, then you get an elliptical paraboloid. So let's practice all that. Equations. Let's practice that in the equations. So we're talking about paraboloids here. Here's our kind of reference paraboloid, the one we just did. It's kind of like our y equals x squared in R2. And from there, all right, so we got that. Said that already. Traces for z, particular traces for a constant z are called level curves. All right, so here's, did I fix this or not? Yes, I did. I fixed it. Okay, so here's a bunch. And again, we could change the direction in which it opens. We can stretch and squish it and make it elliptical, or we can translate it. And so we can see one or more of those adjustments to all these. So can you sketch and make verbal descriptions of all these? For instance, I think we just talk through them. Ready? So this one, how is it going to be different from ours? It's going to open which way? Opens in positive x direction. Did I say y? I meant to say y. Opens in the positive y direction. I don't know what I said. Okay, that means it opens to the, what? Which way? To the right. Is it circular or elliptical? Still circular, and opens the positive y. And its vertex is where? Still 0, 0, 0. Okay, this one. Circular or elliptical? Still circular. Origin? Or sorry, vertex? Origin? This one opens which way? Negative x. So it's origin. So it's vertex to the origin. It's going to open behind the screen, right? Open away into the wall. Okay, this one. Vertex. Still the origin. What's different about this one? It's elliptical. So this is going to be z equals x squared over 3 squared plus y squared over 1/2 squared. So it's going to still open which direction? It's going to go open up, but it's going to be stretched in and out of the screen by 3 and smushed in the y direction by 1/2. So it's going to, can you imagine that? So it's going to be much wider in the x direction in and out of the screen, and then it's going to be flattened left and right, and it's going to open upward. Okay, let's just skip to this last one here. Which way will it open? Positive. Opens in the positive y. Vertex is at? Try again. -1. -3. 2 is the vertex. Everyone see that? -1, -3, 2 is its vertex. And then it's elliptical or circular. Elliptical, and it's going to be stretched. Yeah, it's so the ratio of radii in the z to x direction is going to be what, 5 to 4. So those radii in the z direction, they're going to get bigger. In the x direction, the radii will get bigger, but the ratio of your radii will always be 5 in the z to 4 in the x. So this is an elliptical paraboloid. Okay, so you got today's web work at 5, another web work for Wednesday at 5. You got your written homework due Thursday. I think I made it midnight. You're going to submit online. And then we got the exam Friday.